Imagine you have a box, and out of that box is radiating a bunch of electric field lines. So out of that box is coming out some sort of electric field. Electric field is leaving the box. It's leaving the box from all directions. It's leaving from all directions. Could you tell what was inside this box just from the electric field? To some extent, yes. Because the electric field is leaving the box, moving away from the box, we know that there has to be some sort of positive net charge in there, because a positive charge is what causes an electric field to flow away from it. If there wasn't a positive charge in here, there would be no electric field, and nothing pushing the electric field out of the box. So there must be a positive charge. And we know that purely based on the fact that there's electric field flowing out of the box. Flowing out of the box here. So what do we call this concept of electric field flowing through a box? We call that concept electric flux. Electric flux. This word flux here is just synonymous with flow. Whenever you hear the word flux, you can just think of a flow coming out or through a surface right here. So we have an electric flux. Can we generalize this idea a little bit more? Sure. So most of the time we probably won't have a box, and even most of the time we don't want to have a box because it's just mathematically hard to deal with. But maybe we'll have some more general shape, like this squiggly surface right here. And I know I'm drawing it in 2 dimensions, but really this should be more so thought about as some 3-dimensional surface, like the shell of a sphere or something like that. This is some wonky 2-dimensional surface blob floating in 3D. Alright. Now, once again, if we have some sort of positive charge that is encompassed by this surface, then we know that electric field is going to flow out through the surface. It's going to exit, and there's going to be what we call positive flux. Whenever something is leaving the surface, flowing out, that is when flux is positive. So, whenever you have this Q is our enclosed charge, Q enclosed, whenever that is greater than 0, whenever it's positive, whenever you have a positive enclosed charge, then your electric flux, which we symbolize using this capital Phi and subscript E for electric, your electric flux, will also be greater than 0. Positive enclosed charge, positive flux because it's flowing on out. Now, if we were to say that, hey, we don't have a positive charge in here, let's say we have a negative charge. Let's say we have some sort of negative charge. Have a negative charge in here. Well, then now it acts like a sink. Now it acts like a sink with electric field flowing into the surface, flowing into this object towards the charge, right? Because if you were to put in a positive test particle, it would be attracted to the negative charge inside of here. So overall, the electric field line should point towards it. So if your Q enclosed, your enclosed charge, if your enclosed charge is less than 0, then your electric flux will also be less than 0. Also be less than 0. All right. Well, what significance does this enclosed part have? What does it matter that the charge in here is enclosed? Well, let's examine that by using a scenario where there is no enclosed charge. Let's say within this space here, we've got some sort of surface, some sort of analogous blob, And there's nothing in here. There's no charges sitting inside the surface. But there is some electric activity happening either on this side or on this side. And we don't exactly know what it is. We don't know what's causing it. But we do know that it's forming a uniform electric field that flows from the left to the right. So there's no internal or enclosed charge, but there are charges that are forming an electric field to pass through the surface. What does that mean for the flux? Well, let's split this guy in half here to examine it a little bit better. On this side, it looks like the electric field is flowing on into the surface, right? It's entering the surface. Well, as we saw here, whenever it's entering the surface, whenever it's entering our enclosed object, that means that the flux is negative. So right here, I'm going to denote this as flux 1. That is less than 0 over here. Now on this side, it looks like it's leaving the surface. It's leaving the surface. Whenever it leaves the surface, we know that we have a positive flux. We have a positive outward flux. So our flux 2 is greater than 0. And now to find the total flux, we just want to add together, use the superposition principle. We're going to add together both of our fluxes. So we've got flux 1 plus flux 2. And overall, what's that going to equal? We've got a negative number here for this one, and we've got a positive one over here. And look what's happening. Whenever an electric field line enters through, whenever there's an electric field coming in, it has to come back out at some point because it's moving this way. The object isn't going to stop the electric field. It's just going to lay there and let it pass on through. That means for every negative flux, there's got to be an accompanying positive flux that cancel each other out. Meaning that overall, we're left with 0 total flux. 0 total flux. If we have no enclosed charge, then we have no electric flux. The only charge that matters is the one that's enclosed inside here. All right? Now, what if we have more than one charge inside of here? What if we have a system of charges? Let's say we've got some sort of dipole. So we've got a positive charge sitting right over here. And we've got a negative charge sitting right over here. What's going to happen? Well, we know that right in the middle, the electric field is going to flow from the positive charge towards the negative charge. The positive wants to go to the negative. It doesn't pass through the surface at all, so that's pretty nice. Now what about over here? It flows on up from the positive charge, but as it gets farther out, it gets more and more attracted to the negative charge, or more and more affected by the electric field of the negative charge, and it comes back in. Same old thing in here. And then that'll also happen from behind this charge. And overall, every electric field line coming from this positive charge will end up being terminated on the negative charge. So something that you can notice is for every exiting electric field line, it ends up re-entering at some point. See, exits here, re-enters here. This will exit somewhere about here. It'll re-enter here. This exits somewhere around here. Re-enters here, exits again, and then re-enters. So overall what's happening is your flux right here, you've got a positive flux because it's leaving, right? But then a negative flux because it's got to re-enter. And overall, your flux is equal to 0 because your net enclosed charge is also equal to 0. There is charge in here, but they cancel each other out, leading to have a total of 0 electric flux. So hopefully that helps you understand the concept of flux a little bit. It's basically just the measure of how much electric field flows through a surface, whether it's leaving or coming in, leaving and then coming back in, whether or not there's no enclosed charge at all. All you've got to remember, positive net enclosed charge, positive flux. Negative enclosed charge, negative flux.